I'm Harshda Saxena. I'm an undergraduate at IIT Bombay, and today I'll be talking about, forget the mouthful, basically just the impact of modified gravity theories on structure formation in a context of kinetic field theory. So before I start, I would like to thank the organizers of the conference for allowing me to speak at this conference. It's a great honor. Secondly, I would like to thank Professor Matthias Bartelmann, who firstly facilitated this entire project, and his entire group, Alex, Johannes, Ricardo, and everybody else at Heidelberg and beyond. So firstly, firstly, I'll start out with the motivation of why we really care about this. There are a lot of deep and dark questions that have been plaguing humanity for a while, especially in the context of structure formation, which have been, how do nonlinear structures form and evolve? And is there a first principles approach to study structure formation? Now, for those of you who attended the cosmological perturbation theory lectures, we know that you can model dark matter density as a fluid, and we have a pretty good idea of the linear structure formation. But once things start to go out of hand, when we move into the nonlinear regime with the whole density perturbations and what is called the shell crossing problem. So the way people solve it is basically using n-body simulations. So this was a starting point where Matthias and his group started to think about what if we do a statistical version of the same, which brought us to the point of kinetic field theory. So that kinetic field theory is basically a statistical field theory for classical particle ensembles, which basically means now that you live in phase space. So you don't have this problem of shell crossing anymore. So it's basically a Hamiltonian problem. So you just have an initial condition, you use Hamiltonian dynamics to sort of evolve the trajectories. The main thing which has the information of everything in kinetic field theory and the information of your entire system is what is called the generating function in Z, which you can just basically think of as a generalization of your partition function from thermodynamics. And it looks for general cases looks something like this, the Z over there, and where PQP is sort of like the initial probability density. If you solve this, you will basically, through Hamiltonian dynamics, and J is sort of the generator fields, you will get that the equation of motion is basically some inertial motion plus the interactions, which is basically what we want to model. So kinetic field theory is something which is completely general. I remember attending a talk where some biologists used KFT to study structure formation in cancerous cells, but I think we should stick to cosmology here. So we can write out our equivalent Hamiltonian as the first line, which is basically a mass dependent as a function of the mass, which is time dependent in our case because co-moving coordinates. And we have the Poisson equation. We can also choose the main point that we'll be doing is choosing our time as the growth factor, because we want to see linear growth and then we want to see deviations from that linear growth. So once you work out the entire math of KFT, I'm just putting the results there because KFT is too huge for me to cover in the tiny time. You get that the Q of T is basically the linear Zeldovich trajectories, and the deviations from those Zeldovich trajectories are basically governed by this function phi, which basically which is sourced by the nonlinear density fluctuations, which is pretty convenient once you think about it. You have Zeldovich trajectories, and the deviation from those trajectories are sourced by what you want, which is the nonlinear density fluctuations. You can go a little bit further. You can define what is called a density operator, which is basically the Fourier transform of the individual delta functions. And from there, you can get the 2-point power spectrum or density, which is basically this, evaluated at the generator field 0. From here, you can also get the 3-point cumulative, 3-point functions and the bispectrum and so on and so forth. But we'll be focusing on this over here. One thing which, so now that we finally want to encode interactions is using what is called the interaction. You can define interaction operators and do the same thing. I'll not go into that. But the final result from all the math of KFT is that the nonlinear power spectrum depends on the linear power spectrum with the interaction operator, which looks something like this. So forget about all this. The interaction operator basically encodes, is a function of the convolution of the one particle forces, so the one particle potential, which is V, and the sort of density over the initial, the linear powered spectrum of the particle. So it's how do you affect each other is basically, the interactions between particles is basically the forces between them, along with how they are distributed in space, which makes sense. So just to build in the fact that this is related to reality, we are grounded in reality in some way. You can see that this is the linearly evolved power spectrum, and the KFT power spectrum is actually pretty close to what we expect from numerical simulations of spherical collapse models. You can see over here it agrees pretty well up to 10 H megaparsec inverse, after which the mean field approximation starts to fail. So on to the main topic of the talk, which is on modified gravity. So there has been a lot of work done in the last couple of years on encoding dark energy as a sort of large-scale modification of gravity. But one thing that we need to make sure is that you need to have screening mechanisms, because GR works well on tiny scales, say solar system and so on, because GPS works, we don't fly off hills. So you need to make sure there's some mechanism to turn from this large-scale modification to this to GR, and that is what screening mechanisms encode. And there have been a lot of work on this, but we'll be working with Hassani et al. And Ramanujan's work on the modified Poisson equations can be in this modified theory of gravity with this effective scale-dependent gravitational constant, which they get from simulations. So these are dependent on a bunch of parameters. A is basically 1 if you want to tend to GR again. Capital B, small a, small b are functions of the model. So depending on what model you use, depending on what the screening mechanism you want, you can change the functions of these are the number of screening mechanisms, and these are basically the function of the model. K star is sort of something that parameterizes your screening wave number. So it's basically where you change from modified gravity to the GR. And this is the kind of simulation that we got. So the boxes are basically where the solutions of the numerical codes and of the spherical collapse models, and this is using this sort of parameterization, so that works pretty well. So what we will be doing is, as a first approximation, we'll be fixing our growth factor as the ΛCDM one, and the only effect of this modified gravity will come between interactions. So the interaction operator, which was a convolution of the one particle force, which is basically a Yukawa kind of force, along with the power spectrum. So once you do a convolution and you have a scale-dependent effective gravitational constant, your interaction operator would look something like this. And we've plotted it for NDGP models, which is a special kind of modified gravity model where apparently our four-dimensional world is embedded in some 5-brane world model, and you have some crossing parameters and stuff. But this is how the power spectrum, the relative power spectrum looks like. And you can see the strength of the variation and sort of where it turns over depends on our screening wave number, as it should. The screening wave number. So yeah, K star, which also encodes at what scale you start to change. This is with KFT. This is with KFT. Yeah. So finally, another thing that we've been working on for a while is using Keller approximations to make our life easier. So what we would expect, because ΛCDM is pretty nice, we would expect tiny perturbations around GR. So you would express our nonlinear power spectrum as a functional first order Taylor approximation around GR. So if you have a change in effective constant G, as you do in the models that I just talked about, you can do it sort of as a first order Taylor approximation. Why is this useful? Is because this functional derivative of the power spectrum, of the nonlinear power spectrum with respect to G, can be evaluated at GR. So that's it. You just need to do this once with the models that you already know with GR, right? So basically, if you give me a delta G of any modified gravity model you can dream up, you can interpolate it. I don't care. As long as I have a delta G, you can give it to me, and I can basically spit out the nonlinear power spectrum that we expect from simulations. Just to give you an idea of how this power spectrum looks like, if you plot the change in the interaction operator at some fixed K and say today, with respect to the change in the gravitational constant, so basically you're introducing a change in the, you're modifying the gravitational constant at some perturbance wave number alpha and some perturbance scale factor X. So the change in the interaction operator is dependent on this, and you can see that if I want to evaluate the change at K equal to 1, I should introduce the change in the gravitational constant at K equal to 1, which makes sense. And also, if I introduce it very early, if I introduce delta G just very early in the beginning and leave it there, and since it's linearly evolving, the power spectrum won't change that much. But if I introduce it later hand, it will sort of increase. But again, if I introduce it very close to today, it won't have that much time to settle in and change the interaction actually. This is a similar thing, and I don't have time to talk about it. It's the exact same thing, basically. So just to tell you that the Taylor approximation is indeed good enough. We've cheated here a little bit because we have taken only tiny, we have fixed our parameters of K star so that we only have tiny deviations from GR. So you can see that the exact thing from what I did before, which is this, versus the Taylor approximation, which we talked about right now. They actually agree pretty well for all these models, which is NDGP with Weinstein screening, camouflage screening, Yokawa screening, and chameleon screening. And this is the sort of the functional derivative in full gory glory. And another thing which I just wanted to mention is something that we're currently working on. Yeah, which is something that we're currently working on, which is that if you remember, we just introduced our changes only in the interaction term. So we fixed the lambda CDM. But of course, if you have modified gravity models, you would also change your linear growth. And if you want to evaluate it only in the because if you do it the full thing in KFT, it becomes complicated. So you want to do it only as a Taylor expansion. So you will also have this additional derivative of the growth factor with respect to the G. And you would have to include that in your power spectrum, because your power spectrum, of course, depends on the growth factor. And you can solve that using this thing which Alex and a bunch of others have already done. Another thing, if you want to start comparing with observations, is because now that your growth factor has been affected by the modified gravity model, your amplitude of the linear power spectrum would also change, because that's just d plus squared into the initial power spectrum. And once that changes, you already know from observations what the linear power spectrum looks like. So you can sort of change it by this amplitude so that it starts off beginning differently and it eventually grows to the same thing that we observe today. So using this, we can sort of try to compare with observations and derive constraints on the parameters of these modified gravity models with the expected spectra and the observed spectra, but that's relatively in the future. So just to summarize, KFT is an analytical particle-based approach for nonlinear structure formation using generating functionals and mean field approximations. You can have a large-scale modification of gravity, which will give you, with screening mechanisms, which will give you an effective gravitational constant, which depends on scale. And you can compute the power spectrum of these as predicted by KFT. And we know that KFT agrees pretty well with simulations and is very, very comparatively much faster. And you can also use a first-order Taylor expansion if things get too hard to compute deviations from GR in a wide class of modified gravity theory. So yeah, thank you.
Actually, I'm just trying to connect this formalism to say the effective field theory of large-scale structures. So can you go back to slide 7? Are you assuming that that interaction term you're writing down is the lowest order one? Is that why that's d plus square?
Yes. So if you do the whole thing, it comes like 1 plus iota SI plus so on and so forth. So it's
I think I see the thing.
Yeah.
Maybe I missed this, but so the KFT is very interesting formalism as we discussed to describe the nonlinear interaction. So if you go to modify gravity models, did you compare? So it'd be very useful to compare also to n-body with full modified GR to see whether the formalism is robust. So did you do these comparisons?
Yes. So
this fully, beyond GR.
Yeah. So if you look at this, for example, this is the plot which I showed in a hurry, which was by Hassani et al. And Lombrizer. So they have actually modeled. So this is for Yukawa screening, and this is for NDGP screening. They have shown the sort of the expected model from spherical collapse models. And if I haven't shown this here, I can show you this later. It's not in the slides right now because I didn't have that much time. But if you normalize it to the scales that they have normalized, I mentioned that you need to, if you want to compare and if you want to include the changes with D plus, you need to normalize it. Sorry. You need to normalize it with this factor. So once you include this and do the whole Taylor expansion thing, you actually do end up with very similar power spectrum.
And that's the residual. What is this B?
B is just the sort of this constant. So they're trying to, what they do is that what Hassani et al. Do is that they have spherical collapse simulations for say some NDGP model. And they're like, okay, what if our gravitational constant was parameterized like this? Can I get the parameters like that? So for all these parameters for the models that we use in our KFT calculations, they've gotten from fitting it to the,
It's not a full n-body. This is like a halo model.
This is, I think, spherical collapse model.
Spherical collapse. Okay.
Yeah. So they capture deviations, and then you can see the exact form of A and B. And if using these B equal to 3 parameters, if we do it in KFT as well, we get pretty good agreements. Yeah.
That's what you're doing, yeah. For different, so of course you have to look at different possible models. I think it would be good to do compare with full simulation. Yeah.
So if I understood correctly, you do need delta nonlinear to get the trajectories, right?
I do what?
You
Sorry.
do need delta nonlinear to get the trajectories.
No, so we do have a form of so the nonlinear power spectrum depends on the linear power spectrum, which you already know pretty well from.
But how do you get that SL, SI?
It's from the formalism of KFT. I can talk about it more later, but it's an extremely detailed calculation using.
So nowhere you do need the delta nonlinear, right?
No.
You don't need any information from
No, the delta
simulations.
nonlinear is, so once you have the 2-point cumulants of the delta nonlinear, you get this power spectrum. And this power spectrum depends on the linear power spectrum and this interaction.
But okay, fine, I understand. But then what Arka was asking is that this is still the first order or the 0th order term in the expansion, okay? Do you need 0th order term, right?
It's the first order term in the interactions.
Correct.
So the interactions, yes. So it's sort of like a mean field averaged approximation.
So do you need to worry about the next order correction term in this formalism?
We have been working on better
like
ways.
How large or small could it be? As
Right,
to
right. So you can see from this thing that it doesn't affect too much. Because but once you start to go after a certain wave number, the mean field approximation.
No, why I'm asking this is because in the context of the LSS of the effective field theory of large scale structure, remember when you start adding the higher order terms, the power spectrum goes up or down, and you really need to fine tune the terms that you need to order to make it consistent with, let's say, n-body simulation. Correct.
Yeah.
So will that sort of the same thing happen here, in the sense that if you add next order terms, will it go off and on, and
yes, a little bit.
Okay.
Okay, if there are no more questions, let's thank all the speakers for this session.